Okay, so the sound is on just in time for me to mention the legal disclaimer I need to include. This is our research projects, not a statement about formal benchmarks or company products. So the kind of setting that we're thinking about here is doing graph analytics on large data sets, by which I mean billions upwards of edges and vertices. So data that might take multiple terabytes of DRAM to hold, and we're only interested in solutions in this case that hold the data entirely in main memory. So the kind of data that might come from trawling a social network, looking at internet clickstream data, looking at data sets coming from large numbers of devices. And this kind of problems are a good fit for parallel processing, of course. And if we think about algorithms like PageRank, I'll come on in a moment to an example of that if you're not already familiar with the algorithm. It's possible to process data associated with each of the vertices independently. So we've got a vast amount of work to keep processors busy. And if we're thinking about a cluster of a few dozen machines or a machine with a few dozen sockets, there should easily be enough work to keep a few thousand hardware threads occupied. But as I'll show, we have a lot of complexity that comes from the kind of access patterns that we see when traversing a graph, and in particular in the extreme cases of a social network graph, with the kind of issue that we heard about just now. If we compare Barack Obama's followers with my own followers on Twitter, there's many, many orders of magnitude mismatch. So if we just look at PageRank initially as an example to provide a bit more context about the kind of algorithms that I've got in mind. What we're doing here is computing a value for each of the vertices in the graph to indicate in some sense the importance of the vertex. And the idea is that the central vertex here, the number 10 that everybody's pointing into, will become an important value and get a high value, and some of these peripheral vertices will get a low value. So PageRank does this by starting with an initial estimate, and I'm simplifying this just using the same value in every vertex. And then for every vertex in parallel, computing a new update to that estimate by looking at the incoming edges from it and associating some of the score of the source of those edges as kind of adding to the prestige, you could think of it as, of the target. So a popular vertex, like the one in the middle here, will pick up some of the score from many of the neighbors around the edge. If a vertex has a few outgoing edges, then it shares its score across them, so the 10 on the right there is contributing proportionately less. And then we sum the values together. And there's more steps I'm going to miss out for the sake of brevity, but that gives us a new PageRank value, and we update the score in that vertex, do the same in parallel to all of the other vertices, and then move on to the next step. And iteratively, this is going to converge to a value for each of the vertices. Now, we've got three challenges, as I've alluded to. There's simply the size of the graph. And if we're looking at a modest machine, then we need to figure out how we're going to store that. We need to either distribute the data across enough machines to have enough memory in aggregate for them, or we need to simply have a big machine that can hold the data. We need to handle the fact that if we're looking at a social network graph, then not only do we have this disparity between the popularity of some nodes versus other nodes, but we're also effectively having random links between the edges, between the vertices, sorry. So it's not like a road network graph where you could reasonably efficiently partition this into, say, the local road network within Bristol, the local road network within London, and some roads in between. We can't cut the social network graph up so cleanly because we've got a lot of links for all kinds of arbitrary reasons between these pieces. And those lead to random access patterns, both in the single machine optimizations I'll talk about, and also in the cluster implementation. And of course, many parts of computing is optimized towards predictable, straightforward sequential access patterns rather than these kind of random accesses. And then the final piece I'll mention is the difficulty of load balancing. And this comes back to the Barack Obama problem. The fact that if we have one of the processors in a machine taking sole responsibility for that vertex, then it could well be that that processor is busy finishing off its work while all of the other processors are completely idle because they've finished all of the more straightforward vertices in the system. So I'm going to talk about two ways we've tackled these graph analytics problems like PageRank. The first one is some work we did in the group in Oracle in Cambridge, looking at scale-up processing. So meaning taking a single machine and looking at how we can exploit the hardware efficiently as we go towards the largest machines that we make at the moment. In this setting, the kind of issues we care about are placing the computation and the data efficiently within the machine. So we have an internal network within the machine, providing a cache-coherent address space, but we've got different access times based on when a thread is accessing memory attached to its local socket in the machine or attached to a remote socket in the machine. And we need to take that into account and try to optimize for the distribution of memory. Then in the scale-out setting, which colleagues in the US have been working on, we're looking at a cluster of machines and distributing the data across all of the machines in that cluster and having communication when threads running on one machine want to access a portion of the graph that's stored on a different machine. So we're concerned about these locality concerns as well. We'd like threads to be accessing data locally as often as possible, but we also have to be concerned about making efficient use of the network between the machines. And even though we're using an InfiniBand network in this case with, I think it's 56 gigabits per second on each of the ports, we need to structure the communication to make the most useful use of that available bandwidth as we can. And that affects how we write the software on the machines that are doing the communication. So I'm going to talk a little bit about these two cases, the scale-up one first and then the scale-out, and then come on to some concluding observations about some of the trends I'm seeing in these areas with graph analytics and some of the techniques that we needed to use in order to obtain good performance. So let's look at the scale-up case first. And the machine we're targeting here is the Spark M716. And this is a system with 16 processors. Each of the processors is fitted with 32 cores, and each of the cores has 8 hardware threads. So you multiply the numbers together, and you've got about 4,000 hardware threads within the machine in a single cache-coherent address space. And the particular system we were using has 8 terabytes of DRAM, 512 gigabytes installed on each of the sockets, and 16 DDR4 memory channels on each of the sockets. And a lot of the complexity we have in getting good performance on this system comes down to how the graph workload interacts with the memory system, because we need to keep good utilization of all of those different memory channels if we're going to obtain good performance. We want to avoid there being hot spots on one particular part of the memory while other parts are underloaded, because the hotspot will then limit the overall progress of the complete workload. If we look at the characteristics of the graph workloads in this machine, we can see that, in principle, it's a good fit. We've got the ability to hold data sets up to a significant size, as multi-terabytes. We've got a large number of hardware threads, which we can employ in doing parallel computation of different vertices. And also the fact that we have 8 hardware threads in each of the cores should give us some ability to tolerate the latency of going to memory or going to remote memory in this machine by letting the core switch between these hardware threads while waiting for one of them to have cache misses serviced. So this was one of these pieces of work where when we started, it was expected to be a couple of weeks configuring our test harness to run for this machine, and then we should run the results, get a nice straight line scalability up to the full load of 4,000 hardware threads that the machine provided. And instead, it turned out to be several months' work as we analyzed the workload in more detail, understood a bit more about what was going on, and what was actually happening as it interacted with the hardware. I'm going to talk about some of the directions we explored here, and also some of the dead ends that we went down, perhaps in the hope of avoiding those in the future. So let's start by going back to the Pagerank algorithm and seeing how we structure this in the case of a single scale-up shared memory machine. And of course, this is omitting a lot of the kind of concerns that we heard about in the previous talk. We're just looking at the structure of the graph here and the PageRank values. We're not holding more general properties associated with vertices or edges in this case. So what we do for the representation of the graph is use what's known as a compressed sparse row representation. And here we have 2 large arrays holding information for each graph vertex at the top, and then information for each of the edges from that vertex next one down. And if we look at a particular vertex, just numbered sequentially in ID order here, then the entry in the vertex array provides us with an index into the edges array. And then the bulk of edges between one vertex's index and the next gives us the adjacent vertices to that one that we're processing. So the idea here is that we can represent the graph in a compact way with one word of storage per vertex, one word per edge, and then at least when we're doing the traversal and looking up this list of edges, we've got a nice sequential memory access pattern as we iterate through that array. Then for PageRank, what we need to do is do some processing and access the previous value for each of those neighboring vertices. And the way we do that is we have a third array, the current values, holding the current estimates for the vertices. And we use the IDs from the neighbors as indices into this array, read the current PageRank estimates out of that, sum them together, do some scaling, and generate a result at the bottom. So what's going to be happening here is that we've got 4 main data structures in memory. We're making sequential accesses through the first one, sequential accesses through the second, and then random accesses as we pick up these values dependent on the structure of the graph before making a single write into the target array. And there are 2 main challenges then, which are handling this array here, the edges array, which is large, because we'd expect there to be many more edges in a graph than we'd have vertices, so we've got to pay more attention to that array. But then there's also this hot array, the current values, where we're probing into that based on the structure of the graph, and because we're accessing these elements once per edge, and there's only the number of vertices elements in it, we'd expect this to be more hot. We'll be going to Barack Obama's vertex many times over, and we'll be going to other vertices probably at least once, maybe somewhere in between. So we've got this kind of distributed systems challenge, even though we're thinking about a single machine, because we need to take these arrays within the processor's address space and decide how to map those onto the physical memory within the machine in an efficient way. And the way we could picture this is we've got the address space at the top with these 4 arrays, the vertices, the large edges array, the hot current values array, and then the output array. And we have to go through the interfaces provided by the OS to control the allocation of these pieces of memory onto the different sockets and the granularity at which those allocations are handled by the page tables. So this, by doing this effectively or doing it poorly, we can start either creating hotspots within the memory system if we end up with too much of the hot array directed to a single memory socket, a single set of memory channels, or we can do it well and disperse those accesses across the whole machine. So we tried, first of all, to look at what happens if we just use the OS defaults. We let the OS place these allocations onto different pieces of physical memory, in this case split, let's imagine just for simplicity, between 4 sockets in a machine. And we then look at what happens as the system runs, given the actual distributed nature of the internals of the machine. If we look actually at what the system is like, we've got, in fact, the sets of 16 processors are split into banks of 4 sockets into these units called a DCU. And then we have a memory system that's fully connected between the sockets in the DCU, and then a switch internal within the machine that handles the interconnect between DCUs. So we've got quite a complicated system topology inside the machine with different numbers of hops over this internal interconnect based on where the accesses are happening. So let's look at a couple of simple examples then of how these different graph algorithms perform based on where the memory is placed. And what we're showing here is the time in seconds for just a single-threaded execution. And we're looking at 2 machines, one called a T58, which is an older 8-socket machine, and the 16-socket M7 machine I mentioned earlier. We're looking at 2 data sets. The same data set we heard about earlier from Twitter, which is representing a snapshot of the social network graph, and then a synthetic workload here called Scale27, which is a skewed workload with some very popular nodes, some less popular nodes. But we can control the size of that and generate similar graphs for handling different memory capacities. And what we see here is on both of these machines, the older one and the newer one, we get a big difference based on where the memory is located. The faster red performance here, we're able to put all of the graph structure onto the same socket that's running the single thread. And the slower, darker bar, we're spreading the memory across all of the machine, and so needing to go across that interconnect more frequently. And locality here is getting us maybe around 40% improvement if we're able to handle it well and put all the memory on the same socket as we're accessing it from the thread. But let's see what happens as we run the complete parallel workload instead of this single-threaded one. Because, of course, in the parallel setting, we're going to have the threads distributed across all of the sockets. And so we're going to have some of these be remote from the storage, and we're needing to figure out as well how we should distribute the storage itself. So the first case is leaving it to the OS defaults, which tend to do a reasonably good job of distributing of the memory across the entire machine. So I'll just again use 4 sockets to keep the figures smaller, but we've got some portion of each of the arrays allocated on each of the sockets. Some of them are maybe getting a bit more of one array than another, and some of them are maybe using smaller page sizes than others based on whatever heuristics the OS is using and whatever state the memory system has been left in by previous runs on the machine. And this was the result we got, which was the one which disappointed me and made me think, well, this isn't going to be a couple of days' work. Because we're looking as we increase the number of threads from 1 up to 512 and then beyond. And we're looking at the speed up we've got over sequential execution. And this machine, you'll remember, has 4,000 hardware threads. And we'd expect at least good scaling up to 512, which is the point where we're running 1 thread per core, and then we're using multiple threads per core beyond that. So you can see we didn't get the scaling I'd initially hoped for up to 512. We're only seeing about 200-fold speed up. And we're getting absolutely no benefit from the extra hardware threads that we'd been hoping would let us mask some of the access latencies. So we think, well, let's try to control what the OS is doing a little more and make sure we really distribute the data evenly between all of the sockets. Maybe the fact we gave one socket more of the hot array than another socket has led to some issues. And so we'll distribute all of the storage equally and control the page sizes to the ones we want. We rerun the experiment, and we got a tiny improvement. So this, again, was disappointing. We'd done similar work on a smaller machine with slightly older hardware, and these techniques have been worthwhile. So we think, well, in some of these cases, we've actually got enough memory that we can replicate the data. So if we're happy trading off some memory capacity for more performance, we'll actually take a copy of the graph structure, keep that on every socket, and then every socket can access its own local replica of the graph rather than having to access the graph remotely. So we're wasting memory from that point of view, but we'd hope we get good performance. We got the shared hot array the shared array we're going to update each time through the loop. That's got to be held just once, but the structure of the graph is fixed in our experiment, so we don't need to replicate that. So we do this trade-off for memory and execution time, and you can maybe guess from the context, we don't get as much of a speed up as we'd been hoping. We get some benefit. We're going up now to the stage where it's coming on for 250-fold improvement, but we still don't have any benefit from using extra threads. And that surprised us because we were thinking we were taking load off the switch in the middle of the machine. We'd be avoiding bottlenecks in the memory system, but obviously something else was going on that we'd not anticipated. And then just one last experiment here before we go on to what actually helped in the end, was to re-replicate the data that we're updating between each iteration. So if you remember, the PageRank iterations read the current numbers on each of the vertices, compute a new number for each vertex. And we thought, well, what if we have each thread batch together its updates to that array, and then at the end of the updates, distribute a new copy of all of those to all of the other sockets in the machine. So we're trading off a bit more memory again, and we're adding some extra work to do to copy data between sockets. But that's happening once per iteration of the whole PageRank computation, and it takes a very, very small time in proportion. And we thought, well, now we've got a nice memory layout. We've got very large page sizes, so we're not going to be seeing translation issues with the TLB. Almost all of the accesses are socket local, and it didn't help us much. So we looked at this in a little more detail and probably did what we should have done at the beginning, which was to look at more of the system profiling tools and see, well, what actually is the bottleneck, rather than our misguided intuition that it would be the same as we'd seen on earlier systems. And what we realized was that actually what's happening is that we were being limited by the off-chip bandwidth, even though these processors have 16 memory channels, more than the Intel Xeon systems we were comparing against at the time. And the core in the chips was improved compared with the older T5 system I mentioned. And it actually turned out that the out-of-order execution in the processor was letting us saturate the off-chip memory bandwidth with just one active thread. So the technique that we used in the end to improve this, I'll just go through very quickly, was to divide the graph up into per-socket tiles of structure, but to do that just taking into account the load that these tiles are going to place on the memory system rather than the structure of the graph itself. Because, as I mentioned, the graph may well not be one that can be partitioned up as nicely as a road network. So what we do is we look at the hot array that's causing the problems here. We divide it up equally. Again, I'll just use 4 instead of 16 as an example, and put each of the elements into a separate tile. We then build up a new graph that's going to just be referring to the elements of a given color. So if we follow back from the green vertex here, we color the edge that's pointing to it green, and we then color the vertices at the top according to all of the different edge colors that they have. And the effect of doing this is that we get multiple separate graphs which we can place on each of the tiles. But crucially, each of the tiles now has its own portion of the hot array, which is going to be smaller in size. And by dividing the array up in this way, we get it down towards the capacity of the last level cache on the processor, and we're reducing the demand for off-chip bandwidth by improving the cache hit rate. So we've got some pre-processing to do, and we've got a potential a space cost again, because we're having to replicate vertices where edges have been colored in different ways. But we've fixed the layout of the difficult array, the hot one here, and that's going to be what helps us in the overall performance. So we go through a few steps of building up these separate tiles, and then when we've applied this technique, we get much better performance both at one thread per socket per core, and finally we also get some scaling as we go beyond that and start using the extra hardware threads that the multi-threaded cores are giving us. And we then went back to a full machine looking at the M716. We looked at a graph that was much bigger, so it needs 4 terabytes of memory rather than the smaller Scale 27 and Twitter data sets. And we were actually able to get a superlinear speed up as we add extra sockets of the workload. So we start with 1 socket and then look at performance at 2, 4 up to 12, which was the limit for some other internal constraints we were able to go to. So we had some kind of intuitions here that we had to think about locality in terms of where a thread is placed and where the memory it's accessing is going to be, and trying to keep those together by using techniques like replication. But it turned out that what we actually should have been thinking about was the load on the memory system, getting that spread evenly across all of the channels, and then making the best use we could of the caches in the processor to try to reduce the demand for off-chip bandwidth. And when we did that, we could get much better scaling than our first case. So let's look at the second case study here, which is the scale-out workload, which we developed alongside the scale-up example. And this is taking a different direction. Rather than saying that we'll have a single large machine, we'll take a cluster of commodity 2-socket systems, and we'll distribute the graph across those. We'll distribute the work across the machines, and we'll build a communication and runtime system for handling remote memory accesses when we need to access data that's held on a different system. The particular machines we're using are relatively beefy machines. I'll come back at the end to the motivation for doing this. We've got 2-socket Sandy bridge systems in these experiments. We're using half a terabyte of DRAM per machine and an InfiniBand interconnect. So we can see that the first of these challenges here is handled in a relatively direct way. As long as we're representing the graph in an efficient way and not adding overheads, we're available to scale the available memory to the system with the number of machines that we introduce. But we've got to handle these other issues. We've got to build an efficient way to communicate between the machines, given that we no longer have just direct read and write for shared memory. And we need to handle load balancing to keep all of the machines busy all of the time, rather than risking straggler effects. Now, the first of these issues is one which we've handled by trying to make the performance of the runtime system on each individual machine as optimized as possible, as close to the scale-up system, in fact. And we do this with a task-based runtime system, where we divide each of the pieces of processing for the vertices into a small task for that vertex. So you could think of these as being computing the PageRank value for one given vertex at a time. And then within a machine, we have a work pool with threads that pull batches of tasks off this and then are responsible for handling those tasks, handling the local memory accesses that the task generates, and handling the communication needed when making a remote memory access. The way we handle the remote memory accesses is to build a communication layer that batches together requests for multiple pieces of data that are not held on the local machine, and then aggregates these into a message until we've got a large enough message to send over the InfiniBand interconnect with good performance. And if we were to just send a separate InfiniBand message each time we need to read the connectivity or the PageRank value of a given vertex, then we'd be seeing extremely high overhead. So we need to batch these together until we get 1 or 2K in size of data to make the communication efficient. One of the ideas we use here, which of course not a new idea, is to use the parallelism to mask the latency of that network communication and the time it takes to build a batch together. So what we do is, within a local machine, we build up a message to send to a given target machine, aggregating together all of the requests for data that's going to be held on that machine. And so we have a worker thread ID associated with this. We have a pointer to a buffer that the responses should be deposited in when the remote machine responds. And then we build up a list of all of the addresses that we want to access with corresponding positions in the results buffer for the next piece of that task to resume once the response comes back. Then once we've got a full message, so a couple of K in size, we can use RDMA to transfer that to the remote machine, and then a thread on the remote machine will go through and pick up the different pieces of results there. So there's a couple of interesting things here. We're building up the responses in a batch and sending those back, and then depositing the values into the locations associated with the tasks. We don't actually have any work going on to suspend or to resume the tasks. We actually just keep the tasks in a big circular buffer and then have a worker thread go through the buffer in turn, processing tasks, checking whether their responses has come back or not. And that actually turned out to be an important optimization. It meant we didn't need any thread synchronization on the local machine, managing work stealing queues or anything like that. And because we had billions of tasks, then it's likely that by the time the execution point comes back around, that task is ready to run some more because its last response has already completed. So we put these ideas together, and the next issue that I mentioned is needing to handle load balancing within the cluster. I'll just briefly mention the two ideas we're using here. The first one is we need to make sure that each of the machines is going to be doing roughly the same amount of work, because in the single scale-up case, we've got this shared memory address space that lets us move work between threads and dynamically rebalance the load. Whereas if we've cut the graph into sections and given those to different machines in the cluster, then we're going to find that we can't do that dynamic rebalancing as effectively. And what we actually do then is to make sure that instead of giving each of the machines 1 over n of the graph vertices for a given number of machines, we give them 1 over n of the graph edges, because roughly speaking, the amount of work is going to depend on the number of graph edges that a machine has been given, rather than the number of vertices it's been given. We also find that we need to do load balancing within each of the machines. So we're looking here at the initial performance that we got when we just did basic per vertex balancing of the work between the cluster. And we saw that there's only a tiny fraction, about 10% of execution, where all of the machines in the cluster and all of their threads were busy. And then there's some time when we've got load imbalance because only a few of the machines are busy. And then we've got the final case where there's just one machine, and the threads, even in that one machine everybody is waiting for, some of them are busy and some of them are not. So we actually need to get both of these levels of load balancing working effectively before we were able to get good performance. We needed to distribute the edges evenly between the machines. We then needed to distribute the work evenly between the threads within each machine. And once we had both of those done correctly, we were able to get the kind of performance that we've been looking for. Just one brief performance result. I've got some follow-up slides I can talk about offline, which look at a wider variety of algorithms. But just to give a flavor for the kind of performance we've been aiming for here, the dotted line is the performance we get from running the scale-up system on a single machine in this cluster for a small workload that fits in a single machine. We're looking at the performance relative to 2 machines running an older version of a system called GraphLab. So these results are a couple of years old, so the GraphLab system may have changed if you're making any concurrent comparisons. So the dotted line is our own scale-up system. Then the red line here is showing our scale-out system, and how with 2 machines we've almost paid for the cost of using the communication layer that we've built, rather than using the machine's own shared memory abstractions. And then as we go to 4 machines, we've got an improvement, and we keep scaling up to, in this case, the size of our cluster at the time with 32 machines. And you'll see it's a log scale on the left-hand side, so that's representing a significant improvement, and is also showing that the performance of the single machine version was substantially better than the distributed frameworks we had available to us for comparison at the time. So let me wrap up with a few observations about these 2 case studies that I've worked on, and some of the directions I see for some of these analytics systems in general. So if we think about the single machine case, the scale-up workload, and what we were expecting to see and what we actually found. Well, first of all, I was expecting within our own parallel runtime system, we'd find issues around lock contention and work distribution and general kinds of efficiency improvements we needed. And indeed, we found that, and there was some straightforward debugging of identifying contended locks and fragmenting locks into per-socket versions, these kind of techniques. Memory placement was where we got a big surprise. We were expecting that NUMA effects and promoting locality would be important, given those initial bar chart results I had showing the local versus remote access penalties. But in fact, it turned out that once we'd handled many of these other issues, that hotspots on the individual DRAM channels were most significant, and that we could, given the large number of threads that are accessing the graph and the presence of popular vertices like the Barack Obama node, we'd find that we could easily reach the 100 gigabytes per second per socket ballpark limit that we had on these processors. And so we want to make sure we don't saturate one of the memory channels. We want to distribute the load evenly. And then we were expecting that we would find a good use of the hardware threads in the multi-threaded cores, and that these would let us mask the cache latency. Whereas in fact what was happening was that the speculation and the out-of-order execution in the processors was extremely good for the very tight, small inner loops of an optimized PageRank implementation, and that out-of-order execution was itself sufficient to issue enough memory accesses to keep the bandwidth utilized on an individual processor. So we didn't have effectively any spare bandwidth for extra threads, so instead we had to reduce the cache miss rate and try to find more work by having threads be able to work within locally cached data. If we look at the scale out case, then one of the trends which we realized as we were working on this was that we actually needed to use an efficient single machine implementation as the basis for this. That there were a lot of cases where we built prototypes that seemed to scale well, but could never catch up with the performance of a single machine. And that it was much better for us to focus on having the performance at small machine counts be competitive, given that many workloads are probably only going to need 1 or 2 machines. And so we want the flexibility to keep growing without a big performance discontinuity. And we've seen some observations along these lines. There's a very nice set of blog articles by Frank McSherry, who's looked at some of the different graph analytics systems and compared them to the performance of basic sequential C code running on his laptop. So if you Google for Frank McSherry laptop, he's got a lot of great examples like that. And he was showing that his basic C code was both able to outperform if all of the graph was available in memory on his local laptop, but also that the compactness of data structure representations, like the CSR graph I've talked about here with the arrays representing the graph structure, meant he could actually hold data on his laptop that other systems were distributing in order to accommodate it, simply because he was looking at a more compact representation. So we've tended towards this case of having a cluster of fairly beefy machines using large numbers of threads within each of them, and using this to both keep good utilization within the machine for the CPUs and the memory within each of the cluster systems. And also, because we have beefy machines, to be able to generate a large load on the network between them. In this case, we're just looking at those 2-socket Sandy Bridge systems and the InfiniBand interconnect we were using. And it turned out that the sweet spot was something around using 24 threads per machine in order to saturate the 56 gigabits per second bandwidth we had available. So some of these were results were unexpected to us. We'd not been expecting we needed to use quite such powerful systems in the individual machines and the scale-up in the scale-out setting. Just one final observation, which is that as we progressed with this work, I've come to realize that a lot of the issues we're tackling really have a lot in common with high-performance computing. That a lot of the concerns we're looking at around memory placement, around thread placement, are the same ones that have been studied in many other settings over the years. Issues like the efficient use of RDMA to control the transfer of those requests and responses in the scale-out setting. And that many of these issues have only come to attention in the case of the graph analytics work once we've pushed towards building a high-performance implementation. And when we did initial work on other implementations, we were seeing issues around, say, the garbage collector in the Java virtual machine. And as we've optimized the system and looked at how to represent the data in a single machine, we've come to see these other issues becoming the more dominant factors in performance. Then finally, we've got the other issues which are different to those that have traditionally been seen in HPC. So, for instance, when we're thinking about more complex settings than an individual PageRank algorithm running on dedicated hardware, we need to be concerned about how to manage, say, a graph analytics server managing different users interacting with it at the same time. These kind of OS-style pieces of functionality that would be common in a server setting, but perhaps not in a dedicated high-performance computing setting. If you'd like to follow up some more on the project, the link at the top provides some more details about all of these different pieces. There are some downloads available, and also some links to some of the original research work on the domain-specific language that we use as the input to these algorithms, so that end programmers don't have to be thinking about RDMA and batching and all of the kind of low-level optimizations I've been talking about. We've got a couple of research papers that describe the scale-out version, the Supercomputing conference a couple of years back, and the fine-grained work distribution in the scale-up setting, which I contributed to, again, a couple of years back. And my contact address is down at the bottom there, and we've got a stand at the end of the corridor. I'd be very interested in talking with people, particularly they're focused on the Oracle Startup Cloud Accelerator program. So let me stop there. I'll be here for the rest of the afternoon. Very happy to take a few questions if there's time, or to talk over coffee later. Thank you. Any questions? Yeah.
Yeah, so with Pagerank, you're saying that most of the time that the loop fits inside, the main loop is small enough that you can ignore the latencies involved. But for most other graph functions, is that true of most graph function algorithms?
So in this framework, we've worked on 4 particular ones in the case of optimizing up to the big 16-socket system. And those have often had a similar structure in that there's an outer parallel loop iterating over all the vertices. There's an inner loop iterating over all of the edges. And then there's a piece of computation. So we've often needed to think about the data structure that the computation is working on. So trying to fit that onto as few cache lines as possible, or to separate hot data and cold data. But the actual traversal patterns have been similar across these algorithms. We do have a second branch to the project, which I've not talked about today, which fits with the query language examples in the previous talk. So there we're looking for effectively a pattern within the graph and saying, show me all of the vertices of this kind connected through an edge of that kind to something with this kind and these particular properties. So that's something which may well need differences in the runtime system and show different effects in the memory. A concern in the pattern matching case is that solutions are built up incrementally, so finding matches to just one of the vertices, then expanding out and saying, well, if we have a 2-vertex pattern, then where do we find neighbors of the first match that still satisfy the pattern? And then we can get explosions in the number of partial matches and collapses down in the number of partial matches. So I think in that case, we'd see very different memory system effects because we've got a lot more transient data being allocated and deallocated rather than the simpler case here of iteration over array. So yeah, I think there's a good set of graph algorithms that these observations hold for, but there's probably a few other general patterns that are going to be different in other settings. Yeah, I think exploring some of this in the setting where there's updates dynamically will be very interesting. Now, this provides a kind of boundary for how fast can we go when we're optimizing for one specific algorithm, and we know the structure ahead of time and can maybe think about the placement of the graph into memory. So it's valuable having that, because if we do something else, we can say, well, is that 10% worse or 10 times worse? But I'd be interested in seeing how the decisions change as we have some change in the structure of the graph, or additions or deletions, and how to merge that in dynamically. Yeah. Okay, good. So I think we're done, and it's time for coffee. Thanks.